Section 2.4, Exact Equations. Here in this section, we introduce you to a method for solving a first-order differential equation in the form m of xy dx plus n of xy dy equals 0, which we've seen already in the previous section, this kind of form of differential equations, where both m and n are functions in x and y. If we let z equals f of xy, or simply f, this is defined as a function in both variables x and y, then the differential of f is defined as partial of f partial x dx partial f partial y dy. Keep that in mind. We're going to come back to this and use it. So if we look at solving an equation like this, tan y dx plus x secant squared dy equals 0. It's kind of like by inspection or guess and check. What can go in here, the parentheses? If you differentiate it, you get the equation right above it. So I would guess, I see secant squared, so there should be tangent y because the derivative of tangent is secant squared. And I see an x there, so should be x in here. So by the product rule backwards, that would give you the equation right above it. So if the derivative of a function equals 0, this means that function itself, x tangent y, is equal to a constant. So this means tangent y equals c over x. And if I want to solve for y, that would be tan inverse of c over x, like so. So now we wrote the given differential equation in the form d of f of xy, right? D of f of xy equals 0. That's what we just did. Now, what we can say, we started with the differential equation, this differential equation, and then what we have, partial f partial x dx plus partial y partial f partial y dy equals 0. That's what we have from the equation. And if we compare these together, if we compare them, then this equals to this and this equals to that. So mxy is the partial of the function with respect to x, and partial f with respect to y is n of xy. We'll come back to this again. Definition, let me introduce a definition. mxy dx, this differential equation that I started with, and xy dy equals to 0, call this equation 1, is exact, it says to be exact, if in a region R, call it, in a region R of xy plane, there exists a function f of xy such that partial of f with respect to x is m and partial of f with respect to y is n. Let's call all of this equation 2 for every xy in R. The general solution of the differential equation is given by f of xy equals c. That's what we obtained earlier. Now, any function, so let's write it as a note, any function satisfying equation 2 is called the potential function for equation 1 above. So from previous example that we started with, we start with an example earlier. It was tangent y dx plus x secant square y dy equals to 0 has f of xy equals x tangent y as a potential function. Again, it's a theorem that fxy equals c is a general solution for the exact differential equation, the mxy dx plus nxy dy. Now we introduce another theorem, and this is basically to test for exactness. Theorem said, let m and n have continuous partial derivatives let's call it m sub y and n sub x on an open disk R of xy plane. Then we say mxy dx plus nxy dy equals 0 is exact if and only if the partial of m with respect to y is the same as the partial of n with respect to x. Very important. So if we look at some examples, we need to test for exactness. xy square plus x dx this is m equals xy square plus x, and this is n equals yx square. We need to find the partial of m with respect to y and partial of n with respect to x and see if they're the same by the previous theorem. So when I find the derivative of m with respect to y, this means x is a constant, so x times 2y plus 0, so that would be 2xy. This one with respect to x means y is a constant, derivative of x squared 2x, so that gives us 2xy. Notice they're the same, so it is exact. Another example, cosine y dx plus y square plus x sine y dy equals to 0. So what do we do? Again, the same way. We find the partial m, partial y. This is m. Derivative of that is negative sine y. And we find partial n, partial x, which is derivative of this. That's a 0 plus this is constant, just sine y. So that gives us sine y. They're not the same. Partial m, partial y is not the same as partial n, partial x. So not exact. That's how we check for exactness. Now, how do we solve, let's say, 2xy minus 3x squared dx? This is not separable. You can't separate this. So what we need to do is, first thing I'm going to check if this is an exact or not. So we find partial m, partial y, which is the derivative of this with respect to y, 2x minus 0, and partial n, partial x, which is 2x minus 0. So these two are the same. So they're the same, so it's an exact. And since it's exact, we told you earlier that we have fxy is defined as partial f partial x dx plus partial f partial y dy for the differential. So if we convert them, remember partial f partial x is the same as m, which is 2xy minus 3x squared, and partial f partial y same as n, which is x squared minus 2y. So what we're going to do is find the function f of x, which is the general solution to this differential equation. And to start with this, you can select either one of these partials. So if I select the first one, partial f partial x, 2xy minus 3x squared, and we integrate. Since it's partial x, we integrate with respect to x. In this case, y is fixed, constant. And so what do we get? When we integrate the left-hand side, that will give me f of xy. The integral of this one, 2y stays the same. X is x squared over 2 minus 3, x cubed over 3 plus a constant. That constant, let's call it h in y. So that's any arbitrary function of y. And after simplifying this, the 2's cancel, you get yx squared minus x cubed plus h of y. But we need to find what h of y is to finish up the function f of x. And to do so, what we're going to do is we are going to look at the second part, which is this one we haven't used. We write that down. Partial f partial y was x squared minus 2y. And from this, we can find partial f partial y. X is a constant here, so that will give us x squared minus 0 plus the derivative of this is the derivative of h with respect to y. It's a function of we're differentiating with respect to y. And then compare these two. Compare them. They represent the same thing. So you can say x squared minus 2y is x squared plus dh dy. The x squared cancels, and that would give us dh dy to be negative 2y. But remember, I'm looking for h of y. If I integrate both sides, so dh equals negative 2y dy, integrating both sides, h of y is going to be negative 2y squared over 2, which is negative y squared. Then substitute into f of x y to get fxy. It was x squared y minus x cubed plus h of y, but h of y is minus y squared. So that's what the function we need. Then you can say, therefore, the general solution f of xy equals c can be written as x squared y minus x cubed minus y squared equals c. We can look at another example. Find the particular solution of the differential equation cosine x minus x sine x plus y squared dx plus 2xy dy equals 0. That satisfies the initial condition y equals 1 when x equals pi. To do that, we can start testing if this is exact or not. So we find the partial m partial y, which is 0, 0, 2y, partial n partial x is 2y. So they're the same. So that tells us it's exact. So then f of xy equals what? We need to find what that is. What's the function? So remember, fxy is partial f partial x dx plus partial f partial y dy. So here partial f partial x is the m, which is cosine x minus x sine x plus y squared. And partial f partial y is n, which is 2xy. So from, you can choose either one to start with. If I start with, let's say I want to do this one, get this one, integrate both sides, then f of xy would equal to, x y squared. Okay, we're doing with respect to y, this means x is a fixed, so this means plus the constant would be any function in x. Any function in x. Also, we need another one so we can compare them together as we did in the previous example. So in the previous example, we used one of them, we used partial f partial x to get f of xy. And then I differentiated the f xy with respect to the other variable, which is y. So here we chose the second one. And what we did here, we are going to take this function and differentiate this with respect to the other variable, which is x. And that would give me y squared plus dg dx. Now you can compare these together, this one and this one. Compare them. So what do we get? Cosine x minus x sine x plus y squared should equal to y squared plus dg dx. The y squares cancel. And what we are going to do is to differentiate both sides, or you can rewrite it dg equals cosine x minus x sine x dx. Then integrate both sides, you get g of x equals integral of this is sine x minus the integral of this one. If we do it by parts, that will give us plus x cosine x minus sine x, integration by parts. These cancel out, so that gives me g of x, which is x cosine x. That's g of x. From here, I can finalize the f of xy, which is xy squared plus g of x, which is x cosine x. The general solution is then xy squared plus x cosine x equals c. But they give us a particular solution, x pi y1 pi plus pi cosine pi equals c. So this is 0, -1, so pi minus pi is 0, so c is 0. Then the particular solution is xy squared plus x cosine x equals to 0. How about if the equation is not exact? So how do we deal with it in this case? So if the differential equation is not exact, we have something called integrating factor. Integrating factor. So what is an integrating factor? Definition: I of xy, or you can use mu of xy, either one is fine, is an integrating factor for the differential equation mxy dx plus nxy dy equals 0 if the differential equation mu xy mxy dx plus mu xy n of xy dy equals to 0 is exact. So in other words, if you take a non-exact equation and multiply it by the integrating factor, it converts the equation, the non-exact equation, into an exact equation. So, for example, if we are asked to solve or let's say prove first. Let's try to prove that mu of xy equals 1 over y squared is an integrating factor for the differential equation y dx minus x dy equals to 0. To do so, we need to multiply both sides of the equation by the same thing. What do we get here? When you distribute, you go y to the negative 1 dx minus x1 y negative 2 dy equals 0. Now we check for exactness. So if we find the partial m partial y, that's a negative y negative 2, or negative 1 over y squared, and partial n partial y is negative. So x here is a constant. X is a constant. So when we want to differentiate the second part with respect to x, with respect to x here, so the derivative of this with respect to x is a negative x. Derivative of x is 1, and the other one stays the same. So the answer is negative 1 over y squared. These two are the same. So that shows us this is an exact equation now after we multiplied by the integrating factor. And to finish solving this, you do exactly as we did in the previous examples. You do the same thing as we did in the previous examples. So sometimes you can be asked to solve this and they give you the integrating factor right away, not just to check. And then the way you do that, you check for exactness first. Make sure you multiply by the integrating factor both sides, check for exactness, and solve. So the steps, first multiply both sides of the equation by the integrating factor, mu xy. Check for exactness, then solve.